In the past few years, there's been growing interest in the vision community about understanding physical interactions in video, and perhaps even imitating them. The pipelines that accomplish this all depend, at some level, on tracking physical surfaces, because this is a prerequisite for understanding the contacts and forces involved. However, there haven't been algorithms capable of long-term tracking of general surfaces in real video, meaning that these models rely on hand-tuned, object-specific models, limiting their generality. In this work, we aim to give users the ability to start with any scene, select any points they want on solid surfaces, and track them over time, revealing details of how objects are accelerating and deforming. And yes, this is a real output from our algorithm, obtained in seconds. We formalize the problem as TAP, or tracking any point. Given a video and a set of query points on any physical surface, the model must output the locations they correspond to on every other frame where they are visible, and indicate frames where they aren't. Collecting large-scale, real-world data to train such a model is difficult, so we instead rely on synthetic training data, specifically the Kubrick dataset. However, the motions in this dataset aren't very realistic, so we need somewhat stronger inductive biases to encourage the model to rely on properties that transfer across domains, such as low-level texture. Our model is called TAPIR, TAP with per-frame initialization and iterative refinement. The model is a conceptually straightforward, two-stage pipeline. The first stage initializes the track by comparing features for the query point with features for every other frame. This gives us a heat map of potential corresponding locations. We apply a differentiable version of an argmax in order to get a position estimate for each frame. Given this initial noisy estimate, the next stage aims to refine the estimate by integrating information across time. We first compare the features for the query point with features extracted from a local neighborhood around the initial estimate. We pass the full set of similarities into a convolutional neural network, which produces an update to the predicted point location. Now for some qualitative results. For each video, we track densely and automatically remove stationary points. This means we get an automatic segmentation of the scene, and we can easily discern how the objects are accelerating and deforming over time. Again, this is trained entirely on synthetic data, so these results are zero-shot. Quantitatively, our model provides state-of-the-art performance on TAPVID, a real-world benchmark of manually annotated point tracks, outperforming prior methods by a margin of 15 to 20%, with runtime that's competitive with the best. Point tracking has many applications. In this paper, we show how trajectories can parameterize models that generate videos, specifically animating still images. In our two-stage pipeline, we first generate a set of trajectories given an image, and then generate videos that match the trajectories, attending to the relevant image locations in order to replicate the textures. TAPIR provides pseudo-labeled training data for both stages. In this example, we show the input image on the left, and in the second column, we show two different samples of the trajectories that the model thinks are plausible. In the third column, we manually warp the input image to demonstrate what the motions capture. And in the final column, we fill in the holes using our attention-based model. Although this is just a preliminary proof of concept, the results demonstrate that the model can identify parts like the head, tail, and paw and generate plausible motions. In this example, we can see plausible hand motions, which is a difficult case for existing generative models. You can see other examples on our website. We can't wait to see what other applications you can build by tracking any point. In follow-up work, we've already demonstrated that TAPIR enables robust robotic imitation from complex behaviors like gluing from as little as 5 demos, without any manual annotation or CAD models. So to help you solve your own problems, we've open-sourced TAPIR. You can run on your own videos using Google's resources, or download the model to run it online in real time, like we did for our robots. Thank you for listening.